Most people trust fish oil pills for omega-3, but one wild plant packs even more, grown straight from the soil, thriving where crops fail and needing no chemicals. So why did agricultural schools quietly erase it from their lessons? The story is not about a failure. It is about something that worked too well, and the consequences linger in every supplement bottle. Omega-3 is not a single nutrient, but a group of fatty acids the body cannot make from scratch. The main types are alpha-linolenic acid, called ALA, found in plants, and EPA and DHA, which come mostly from fish and marine algae. All three are essential for human health, but they are not interchangeable. ALA is the starting material. Think of it as the raw ingredient. The body can convert some ALA into EPA, and then a smaller fraction into DHA, but most of it stays as ALA. Clinical nutritionists measured this conversion in healthy adults. About 5 to 10% of dietary ALA becomes EPA, and less than 5% becomes DHA. For some people, the rate is even lower. This matters because each omega-3 form has its own job. EPA and DHA are especially important for brain development, keeping inflammation in check, and supporting heart and eye health. ALA, meanwhile, is linked to lower risk of stroke and helps maintain the structure of cell membranes, but its effects are less direct. If you eat plants rich in ALA, your body gets a steady supply of this building block. But to reach the levels of EPA and DHA found in fish or fish oil supplements, conversion alone is not enough for most people. The modern supplement market is built on this gap. Fish oil capsules deliver EPA and DHA directly, sidestepping the need for conversion. Algae-based pills do the same for vegetarians and vegans, but plants still matter. Diets high in ALA are associated with a lower risk of cardiovascular disease, and some studies suggest ALA itself has anti-inflammatory properties. The catch is that the health payoff depends on both the amount you eat and what your body can turn into. The longer chain forms. When nutrition scientists compare sources, the numbers tell the story. A tablespoon of flaxseed oil, for example, contains about 7,000 milligrams of ALA. A standard fish oil pill might offer 300 milligrams of combined EPA and DHA. But only a small slice of that plant-based ALA ever becomes the forms found in fish. That is why direct comparison is not straightforward. Later, when lab charts appear, these conversion rates, 5 to 10% for EPA and less than 5% for DHA, explain why the form and source of omega-3 matters as much as the total amount. This basic chemistry sets the stage for the real question. If some plants provide such a rich supply of ALA, and if they can be grown almost anywhere, why did they vanish from the agricultural spotlight? A single chromatogram can tell the whole story. On one side, the fresh plant sample analyzed by gas chromatography mass spectrometry shows a dominant peak for alpha-linolenic acid, ALA. In 100 grams of these leaves, the lab measured 350 milligrams of ALA. Alongside that, smaller peaks for other fatty acids fill out the profile, but none come close to the ALA spike. This is the kind of omega-3 that plants can actually deliver, unprocessed and intact, right from the field. Now set that next to the benchmark fish oil capsule. The manufacturer's certificate lists 300 milligrams of combined EPA and DHA per pill, the long-chain omega-3 fatty acids most people seek. Yet the capsule's own chromatogram reveals a very different landscape. 2 sharp peaks for EPA and DHA, almost no ALA, and a series of minor compounds. Both samples contain omega-3 fatty acids, but in different forms and ratios. The plant's ALA dwarfs any other fatty acid present, while the capsule is built for EPA and DHA delivery. But quantity is not the only factor. The question of freshness matters just as much. In the oxidation assay, the fish oil pill starts with a low peroxide value, but after a few weeks on the shelf, those numbers climb. Oxidation byproducts measured by TBARS and anisadine values rise steadily over time, signaling the oil's gradual breakdown. This is a well-documented problem. Even with antioxidants added, fish oil is prone to rancidity, especially if exposed to heat or air. Many capsules on store shelves test above the recommended limits for oxidation, which can dull their intended benefits and sometimes even produce off flavors. The fresh plant sample, in contrast, arrives at the lab with virtually undetectable oxidation markers. The natural antioxidants, vitamin E, polyphenols, and ascorbate help stabilize the ALA in its natural matrix. The difference is visible in the numbers. Peroxide and anisadine values remain near baseline, even after a few days at room temperature. In practical terms, the plant's omega-3 fatty acids are protected by the leaf's own chemistry, while the capsules are exposed to the slow creep of time and oxygen. A signed letter from the independent testing lab confirms these results. No supplementation, no industrial processing, just a fresh plant with a measurable omega-3 payload and built-in stability. The lab data does not just support the claim, it complicates the entire idea of what counts as a reliable omega-3 source. If the numbers are this strong, the real puzzle is why such a plant would ever leave the curriculum of agricultural science. In the archives of agricultural extension, a quiet change can be traced through the language of old bulletins and research grants. Early 20th century circulars listed a surprising variety of edible greens, some praised for their nutritional value and resilience in poor soils. By the 1970s, the same plant, once recommended as a forage and kitchen green, had slipped into the weeds section, flagged for removal rather than cultivation. Historians of agriculture point to a shift in priorities. As federal subsidies and land grant funding began to favor commodity crops like corn and soy, plants that required no chemicals or patented seeds lost their place in the curriculum. Extension agents, once tasked with promoting local food security, were now encouraged to focus on scalable, input-driven agriculture. Policy analysts trace the alignment of research grants with market trends. By the late 1980s, competitive USDA funding overwhelmingly targeted crops tied to industrial supply chains. Bulletins that once described this plant as a solution for marginal soils now advised farmers on the most effective herbicides for its control. The reclassification from edible to weed was not the result of a single decision, but a series of administrative choices, each nudged by economic incentives and the promise of recurring sales in fertilizer, pesticides, and eventually supplements. This was a funding-driven shift. During this period, the supplement market for omega-3s began its rapid climb, reaching hundreds of millions in annual sales by the early 2000s. While the plant name faded from extension syllabi, omega-3 capsules filled pharmacy shelves. The logic was institutional, not personal. Funding followed profit, and agricultural education followed funding. The omission became self-reinforcing, leaving a gap where practical knowledge once lived. The plant's name is purslane. Once a staple in kitchen gardens and a familiar sight in old extension pamphlets, purslane now survives mostly as an afterthought, sometimes as a weed, sometimes as a wild edible, rarely as a crop. Yet its strengths are hard to ignore. Purslane thrives where other greens struggle, pushing up through cracks in city sidewalks or spreading across dry, neglected lots. It needs little more than sunlight and a patch of bare soil. No fertilizer, no pesticides, no irrigation beyond what nature provides. The plant self seeds so readily that a single patch can return year after year, even if left untended. For anyone curious to grow purslane, the steps are simple. Scatter seeds on the surface of loosened soil when the weather warms. There is no need to bury them. Purslane germinates best in light. Within days, tiny succulent leaves appear, forming low mats that shade out weeds and hold moisture in the ground. Harvest is as straightforward as pinching off tender stems and leaves, which can be eaten raw in salads or lightly cooked. The flavor is lemony and crisp, a sharp contrast to the bitterness of many wild greens. Purslane's nutritional profile is as impressive as its resilience. Fresh leaves deliver 300 to 400 milligrams of alpha-linolenic acid per 100 grams, more than most cultivated greens, and rivaling the ALA content of some seeds and oils. While the body's ability to convert ALA to EPA and DHA remains limited, purslane offers a plant-based omega-3 option with almost no input costs. Seed saving is easy. Just let a few plants flower and drop their seeds. For those searching for seeds or advice, a network of seed stewards and small growers keeps purslane in circulation, quietly resisting its erasure from the modern farm. Yet even with all these virtues, purslane is not a perfect substitute for fish oil. Its omega-3 comes in a form the body must first convert. And, as with any wild or foraged food, soil quality and local conditions matter. But for those seeking a resilient, nutritious green that asks little and gives much, purslane stands ready, waiting to be remembered. Today, most omega-3 comes in capsules, even as plants like purslane thrive in overlooked corners of our cities and fields. As food systems become more industrial, knowledge that is lost is not easily restored. Sometimes, what is left off the syllabus shapes our diets more than what is taught. What else have we forgotten?